Hi, I'm Kutlwano. Please help me with this question.
Okay, lovely question. It's full of a whole bunch of different ratios and similar triangles. It's also going to get a little confusing, so I'm here to help you. Let's take a look. It says, in the figure, MN is a diagram. Wow, a diagram. I'm pretty sure it's meant to say that it is twice the radius of the semicircle with center O. Okay, that's exactly what I meant. There are two radii here, which means it's a diameter. It's not a diagram. Sorry for that, guys. It is a diameter of semicircle with center O. MN is produced, so the diameter is produced to R, extended to R, such that MN is equal to 2NR. Okay, so again, we have sides in proportion. We've got 1 NR there and 2 over here. RS is a tangent to the circle, so this is RS over here, is a tangent to the circle at S, and RE is perpendicular to MR. So we know that this over here is 90 degrees. MS produced meets RE at E. So they're basically saying that this is a straight line, and therefore this is a big right-angled triangle. Firstly, it says to us, prove that SNRE is a cyclic quadrilateral. Okay, so SNRE is this quad over here. Now, remember, immediately when you're trying to prove cyclic quadrilateral, you need to try and prove one of three things, essentially. Firstly, that all 4 points lie on a circle. We don't have that. We don't have a circle around this quad, so we can't say that. Or you could prove that angles in the same segment are equal. Remember when you have that lovely bow tie shape? Equal chords subtend equal angles on the circumference. We don't have that in this diagram either. Then we can prove that the interior opposite angles are supplementary. We have no indication of angle magnitude, so we're going to have to use the last thing that you can use. Prove that the external angle is equal to the interior opposite angle. Okay, so let's take a look at this. We were given that MN is the diameter of the semicircle. So immediately we know that this angle at S is 90 degrees because remember, diameter subtends 90 degrees on the circumference. Okay, so immediately we can say, because we've got this quad here, SNRE, that we're trying to prove is a cyclic quadrilateral, angle MSN is equal to 90 degrees. Why? Because of angle in a semicircle. And therefore, MSN is equal to angle MRE, because MRE was given to us as 90 degrees. We don't even need to justify that. You can say that MRE is equal to 90 degrees, and it was given. Therefore, angle MSN is equal to MRE, and therefore, SNRE is a cyclic quad. And the reason is exterior angle is equal to the interior opposite angle. Okay. Next thing, it says prove that RS is equal to RE. Prove that this length here is equal to this length here. Okay. Fill in our information, 1 to 2, right angled, and we need to prove that these two sides are equal. The only way to prove equal sides is either used proportion, which we can't really do right now, or you prove that the base angles are equal. Because remember, in an isosceles triangle, if these two sides are equal, automatically these angles are equal. So if we prove the angles are equal, we prove the sides are equal. So let's look at this diagram. Well, immediately I know that this angle here is equal to this angle there because of vertically opposite angles. So I'm going to label this over here. So firstly, we can say that angle TSM is equal to angle ESR, which is this angle here, because of vertically opposite angles. Secondly, we know that because of tan chord theorem, remember, angle between the tangent and the chord is equal to the angle subtended by the chord on the circumference. So angle TSM is equal to angle SNM because of the tangent chord theorem. Lastly, we've just proved that this whole quad here is cyclic, which means that this exterior angle is equal to the interior opposite angle. SNM is equal to SER. SNM is equal to SER because exterior angle of a cyclic quad. And therefore, what we've proved, because TSM is equal to SNM and SNM is equal to SER, that means that TSM is equal to SER, and therefore ESR is equal to SER. ESR is equal to SER, and therefore, because we've just proved that ESR is equal to SER, therefore SR is equal to ER. And don't forget your reason. Sides opposite equal angles. Okay, easy peasy. The last thing, this is where our similarity comes in. Prove that RE squared is equal to MS multiplied by ME. Okay, so how do we even do that? Let's fill in what we know here. Okay, we know that these angles here are equal, that one, and that one. So now we need to try and prove this. Now this is a bit high grade because it's going to use two different instances of similarity. Firstly, we've got these two triangles here. We've got this little right angle triangle that comes down here. And then we've got the overall big right angle triangle. So in triangle MSN and triangle MSN, it would be MRE. Angle M is common. Remember, it belongs to both triangles. Angle MNS, which is this angle here, is equal to angle MER, and that we proved earlier. And we already know that MSN is equal to MRE, proven. Therefore, triangle MSN is similar to triangle MRE. Angle, angle, angle. Okay. Because I'm running out of time, I'm not going to prove why another set of triangles is similar to each other, but I am going to make note that they are. This is a 90 degree. Okay, so if we look carefully, we've got this triangle here, MSR, and then we've got a little triangle in here, SNR. Okay, so we know that angle R is common. We also know that angle MSR and SNR are equal to each other because exterior angle of a cyclic quadrilateral. Okay. Lastly, we can say that the remaining angles. So basically, what we would prove is that triangle MSR is similar to triangle SNR. Okay, so now the reason I've written all of this out, I'm going to write the other one down here so I have ease of access. MSN is similar to triangle MRE. We're trying to find expressions for these sides and we're trying to relate all of them together. So if we're looking for MS multiplied by ME, which is on the right-hand side, we've got MS over here and ME over there. So we'd obviously have to match the arcs, okay? And then also we're trying to find an expression for RE, but remember we proved that RS is equal to RE. So obviously we'd work with the RS's in this expression here. So we'd have to match the arcs. And then we'd work with those ratios, okay? And then ultimately, you'd have to find ratios that correlate to each other. They have sides in common, and then you multiply them together.